Hi. So the goal of this video is to go over the solutions for exam number 2 from the summer of 2025 for EML 3041, which is comp methods. And I start these tests with usually 5 or so true or false questions, where if the question is asking you or providing a statement to you, you need to tell me if it's true or false. If it's true, you have to tell me why the statement is true or prove so mathematically. So some questions might be conceptual, some might involve words, while others involve math. Either way, you need to justify why your answer is true. And then if it's false, you have to also explain to me why it's false, whether that's mathematical or conceptual. But the big thing is I want you to find the thing that would make it true. So for this first question, you see a regression model is given by the equation below. I say the residual at 2 comma 4 is 2. If it's true, we need to prove that. If it's false, we'll find a different answer and then correct it. So for this question, let's do this together. The residual is defined as the data point minus the function value evaluated at the x-coordinate of our data point. Remember, xi and yi are basically indicating the ith data point. In this case, we only have one at 2 comma 4. And conceptually, what we're doing with the residual is we are, let's say I draw 4x minus 2. That is a y-intercept of -2 and a slope of 4. So maybe it looks something like this. And then at x equals 2, this function has a certain y value. This would be f of 2. And then the data point itself may not be on the line. That would be 2 comma 4. And the distance between those 2 points is what ultimately determines the residual. Now, the convention is to subtract the function from the data point. So we have to make sure that we're doing that correctly. So if we're to go ahead and do this, yi in this case, or y1 is 4. That's the y value of the data point, minus xi, which is 2, plugged into the function. 4 times 2 minus 2. This ends up being 4 times 2 is 8, minus 2 is 6. We get -2. This is false. It's actually -2 because of the fact that we're doing yi minus f of xi. Conceptually, at f of x, when I plug in 2, this y value is 6. That's f of xi. The data point we were given is at 2 comma 4. So this distance ends up having a magnitude of 2. But based on the definition, this is yi minus f of xi. That gives us a -2 as a residual, which is why the question is false. The two matrices below have equal determinants. And you can see I don't give you a lot of space here. I'm not expecting you to do forward elimination to get the lower triangle all zeros so you can multiply the diagonals together. That's a little bit of a mess. But maybe there is something we can do that can help us in terms of moving things around. Maybe if you look at these matrices carefully, it seems like one of them is a pivoted version of the other. And depending on the number of pivots, and we can go look at our equation sheet, you can see on the equation sheet, I already circled it from a previous time that we talked about this in class, is that depending on the number of pivots, the determinant of the original matrix will be either equal to the determinant of the new matrix or the negative of it. If we have an even number of pivots or an odd number of pivots, that's what dictates if they're the same side or opposite sides. So let's go back to this one. And let's see if we can pivot some things around. If you look, this row here, 2, 2, 3, looks like it's been moved to the top. That seems like we have done a pivot and we have switched these two. So let's write that and just do 2, 2, 3, 1, 4, 1, 3, 5, 6. This was one pivot. Does this matrix match that one exactly? Nope, we got to pivot again. And looking at our final matrix, we see that the 3 is over here, while in our current matrix, the 3 is on our right. So maybe I want to pivot this column with this column. And if you look at that, it does seem to match if you pivot those two columns. So we'll do another pivot. This will be number 2. And that will give us 3, 1, 6, 2, 4, 5, and then 2, 1, 3 if we do the vertical pivot. And now that does match the same as that. Because we have an even number of pivots, and I'll write down, let's say that this is A, and I'll just call this A prime. The determinant of A prime is going to be -1 to the P times the determinant of A. And in this case, P is equal to 2 because we've done 2 pivots. That means that they are equal to each other, which makes this statement true. And that math is sufficient for me because it's showing me you knew how to pivot. You use that equation to say that they have to be equal. That's great. Okay. Moving to number 3, an engineer wants to create a quadratic spline that passes through n data points. A total of n-1 equations are found by matching derivatives at the inner points. Now, a lot of people in the summer read this too quickly. And in class, we talk about n-1 as being the number of points or the number of equations we get from matching derivatives. However, you have to be very careful about your definition for n. So let's go ahead and just draw a picture for a second. Let's say I give you 3 data points. First off, how many segments do we get? We get 2 segments. One there that I drew in black, and one there that I drew in blue. So keep in mind that I have n data points, n is 3. 2 segments. Now, how many points do we evaluate the matching derivatives at? Well, they only touch at 1 point, so we get 1 equation from derivative matching. Now, in the node sets, I believe I say n segments. If this said n segments, this would be true because we get n-1 equations from that. But I said n data points. So if I have n is equal to 3, I get 1 equation from that. Really, the correct statement is to say n-2. And again, that'll be true for any amount of data points. If I give you 4 data points, segment number 1, segment number 2, segment number 3, there are 2 points where we match derivatives. If we have 4 points, we have 3 segments, we have 2 matches, which is why we end up with n-2. The critical point of the function below is 1, 4. This is just testing if you can do partial derivatives. We have to do the partial of this function with respect to x. If we do that, we will get 12x squared minus, if we take the derivative of this term with respect to x, we will get 3y. And then the last term is nothing. We'll set that equal to 0. And then I will do the same thing with respect to y. This first term drops out. The next term is -3x plus 3 is equal to 0. Again, we're taking the derivatives with respect to y. So this goes away. This will become 3x. If we take the derivative, that's the constant that remains. That'll become a 3. This gives us that x is equal to 1. If you plug it in over here, you get that y is equal to 4. So our point is 1, 4. This is true. Lastly, for true and false, the sum of the missing elements A and B in the matrices below is 6.5. This is just strictly matrix multiplication. Let's see, if we were to multiply, let's say, row 1 and column 1, that will give us -2. Let's just go ahead and confirm that. You get 1 times -2 plus 0 times 0 is -2. That is correct. Granted, there's nothing useful there for us, but just demonstrating the process. If we multiply row 1 and column 2, we should get the element in row 1, column 2. This is going to be 1 times 4 plus 0 times b is equal to 4. That is also true. The b died out, so that's not really helpful for us either. So then let's go and do the third row in the first column, which will give us that 1 there. Negative 2a plus 1 times 0 is equal to 1. This gives us negative 2a is equal to 1. We get that a is negative 1/2. So we got that value found. And now we'll go one more. We'll do the second row in the second column. That will give us that element in row 2, column 2. It's going to be 4a plus b is equal to 5. I now have this negative 1/2 for a. 4 times negative 1/2 is negative 2. We get that b is equal to 7. The question is asking what the sum is. If we add these together, you get 7 plus negative 1/2. That is 6.5. That's true. I hope that's not too difficult. I think that that's not too bad. Hopefully there's no questions on that. If you do, leave a comment or let me know in person. All right. We're changing gears and going to interpolation. They're trying to understand interpolation. If the researcher has 3 data points, what is the lowest order of a polynomial interpolant that can pass through all the data points? Reminder, the big difference between, let's say, interpolation and regression is that interpolation, the function is going to touch all the data points. In regression, we're just trying to get a line of best fit or a curve of best fit that gets close to the data points. But for interpolation, we want it to touch, which means that I'm going to have 3 data points. And I need to figure out what kind of function I can fit in there. One continuous function, not a spline, not separate segments. One continuous function. If there's 3 data points, that means that we have the ability to find 3 unknowns. And the equation that we would use as our interpolant with 3 unknowns is a second order equation. And that's the answer. 3 data points, 3 unknowns. And you can see that here. I gave you 3 data points. I say the researcher collected the points below. Write the systems of equations needed to find the coefficients based on the order in part A. Express your matrix in the form of ax equals b. So again, we have a function that is ax squared plus bx plus c. And I'm going to get 3 equations by plugging in my 3 points. My first equation is going to be based on 2, 1. So I'm going to have 1 is equal to 2 squared is 4, plus b times 2 is 2b plus c. That is what happens when we end up setting, plugging in that point 2, 1. The next point is plugging in 3, 4. If we plug in 4 for y and then 3 for x, we get this. And if we go one more time, we'll see that we get 3 for y. And we get the same exact thing compared to equation number 2. Interestingly, you have x and x repeating. That's weird. We'll see that in a later part of the problem. They said to write it, the system of equations in ax equals b. So what I'll do is I'll create my A matrix or my X matrix and have A, B, and C. We'll have that equal to the right side. The A matrix is going to be 4, 2, 1 is equal to 1. Reminder, that is saying you have 4 times A, 2 times B, and 1 times C, which gives you this. That's equal to 1. The next one's going to be 9, 3, 1 is equal to 4. 9, 3, 1 is equal to 3. And that is our answer for part B. Simply just plugging in the points. I say perform forward elimination on the matrix in part A, the A matrix. So let's go ahead and rewrite that. We just said that that was 4, 2, 1. 9, 3, 1, 9, 3, 1. Nothing was said about pivoting, so we're not going to worry about pivoting unless I explicitly tell you to pivot. Let's go ahead and first let's modify equation 1. We want to eliminate this 9, and luckily our E1 mod is going to be the same for both of the equations. If I do E1 mod, I want the 4 to look like a 9, so I will multiply by 9 over 4. This is going to be 9, 4.5, and then 9 over 4 is 2.25. I'm then going to do E2 minus E1 mod, which is 931 minus that. This is going to be 0, negative 1.5, and then negative 1.25. And that's going to be true for the bottom row as well. So we're going to end up having the same exact thing show up. In both rows, equation 2 and equation 3. Now what we want to do is eliminate this guy, so we can get the lower triangle equal to 0. And in that situation, that already matches the element that's right above it. So our multiplier is 1. All we need to do is do E3 minus E2, or E2 mod after we multiply by 1, but it's the same. Let me go ahead and make this a little bit smaller so I have more space. Nope, I took that with me. Oh well. So if I were to do, let's say, E3 minus E2 mod, that's just going to be 0, 0, 0. Negative 1.5 minus negative 1.5 is plus. That goes to 0. Negative 1.25 minus negative 1.25 will end up leading to 0 as well. So our matrix ends up being 4, 2, 1, 0, negative 1.5, negative 1.25, 0, 0, 0. That is the forward elimination process of our A matrix. Using previously found answers, discuss whether the data allows for a valid polynomial interpolant. Support your conclusion using equations. Well, first off, we have this situation here, AX equals B. And if it was a valid interpolant, we would have a unique matrix for X. We'd have a unique vector for it, which allows us to isolate it, and we know how to do that already. We'd multiply the inverse on both sides of the equation. The issue is, though, if you look at this matrix, the determinant of this matrix is 0. Because if we multiply the diagonals together, that will give us 0 when it's in that specific form where the lower triangle is all zeros. And the issue is that the inverse of A is inversely proportional to 1 over the determinant of A, which means that the inverse is undefined. So basically, this is not valid, not a valid polynomial is possible because the determinant is 0 and the inverse does not exist. So we can't find a valid polynomial interpolant for this situation. That's quadratic, at least. I say here, if the data does not allow for a valid interpolant, suggest a minimal change needed to make it possible. If the data does allow for a valid interpolant, identify a key property of the data that guarantees a unique solution. We know that it's not possible based on our answer from the previous part. And I say suggest a minimal change. Well, if we look at the data, the reason that we have this situation is because our data is not a function. We have these 2, 3 values that are here. The minimal change that I would recommend is that if you just go ahead and change one of these possibly, then you can go ahead and actually find a valid interpolant. Now, are you physically able to do those? It depends on if you have data or you're doing some math problem or whatever. But the point is, we want to change the double numbers. We want to change one of the x values from 3 to something else. Oops, to avoid a 0 determinant. And just to make that clear, if you look at our original equations, we plugged in 3 into this one and 3 into this one, which led these two equations to be exactly the same. And that was our issue. Because no matter what, if we were to subtract these, you would just end up with zeros, which means our determinant will end up being 0 because this element ends up being 0 if we're modifying that third row or eliminating something from that third row. That was problem 1. Problem 2. This is a regression problem. An axial load F compresses a beam with a cross-sectional area A and a modulus V elasticity E. The beam compresses by an amount X. The engineer does not know the length of the beam. So we don't know what L is. But I do give you E and A, and I give you the relationship between force and displacement for that type of situation. The engineer has access to the data below where X is in meters and F is in newtons. And if you look at this equation, this looks like something similar to y is equal to a1 times x. So for part A, I say find an approximation for the length of the beam. This, like I just said, is similar to this form. And we have done this form in class. I don't tell you to derive it, but this equation is on the equation sheet for that specific situation. It's the sum of the x values times the y values divided by the sum of the x values squared. We're going to say that A1 is the summation of xi, and in this situation, y is f. And in the numerator, we'll go ahead and multiply the products together. And divide by the summation of the x values squared. If you go through that math, I get an A1 of 262.7. Now, is that our answer? No, because the question is asking what's the length of the beam. A1 is the same as EA over L. So now I can go ahead and find what L is. I'll go ahead and isolate the L. The E and the A I gave you in the problem as 1,000 multiplied by 4 is the area. If you go through that math and round, you get 15.2 meters. That is our answer for part A. This next question says, estimate the force in newtons required to compress the beam by 0.5 meters. All we have to do is plug in x as 0.5, and then we get the force. F is equal to A1 times x. We just found A1 in the previous problem. Multiplied by a half. If we do 262.7 times 0.5, we end up getting 131.35, but I say to round to 4 sig figs, so this is going to be 131.4. Double check that that also makes sense. If we do it the other way, if I do 1,000 times 4 divided by 15.2. Oh, I did 262.7. Oh, no, that's fine. This is just round off error occurring. This is fine. If you were to use this A1, or if you were to plug in this L into this equation, you would get slightly different answers because of round off, but I would accept both as long as you were consistent. The engineer now believes that the beam is preloaded, meaning a compressive force F naught exists even when there's no displacement. The updated model is the following. So now I have this, where the only difference is, instead of A1x, it's A1x plus A naught, which is a different model. So because it's a different model, our next part says, will the beam length change under this model? And the answer is yes, because we're using a different regression curve. We're using A1x plus A naught now. So since we have a y-intercept, that's going to possibly change the slope, change our A1, and so on. So now I want to find the new approximate length. If we come down to our equation sheet, you can see what our equations are in this situation. A little bit more complicated for the A1. But we'll go ahead and solve that. And if you want to skip ahead past this part, you can, because this part is just strictly algebra. But I'll go ahead and write down what this equation looks like. Double check that that's correct. That is correct. But again, y in this problem is f. So if I really want to be more accurate, I could do it like this. But you'd be fine either way if you did y or f. So n is the number of data points. That is 3. Let's go ahead and calculate the sum of the products, which we already did earlier. It was just this numerator part. So just for the sake of saving some time in this video, I'm going to go ahead and copy and paste this. We'll see how much I actually got of that. That's not terrible. This here. Sorry. This here. Put it there, it's fine. This is the summation of xi, fi. And just based on the solution, so I don't need to do a calculator, also put the n in the front, because that will handle that whole first term. This ends up being 583.2. If we do the summation of xi, which we will just need in general, this will end up being 0.1 plus 0.3 plus 0.8, which to me seems like 1.2 or so. Yeah, 1.2. We'll sum the f values. That'll be 27 plus 79 plus 210. If we go through that, that gives us 316. That will handle this term up here because we're multiplying those products together. And the summation of xi squared is going to be 3 times 0.1 squared plus 0.3 squared plus 0.8 squared. If you do that, this is 2.22. Go ahead and highlight everything and make it a little bit tinier. I'm writing a little too big. And then the last one is the square root of xi, which we already found, and we're squaring it. So this A1 overall will be 583.2 minus 1.2 times 316. That's the summation of x over the summation of f. Divided by n times the summation of xi squared. That was the 2.22. Minus 1.2 squared. And if we go through all that math, we get 261.54. And that will end up being used to find our approximate L, which ends up being 15.3 now. So not a dramatic difference, but a minor difference nonetheless. The last one says find the value of f naught from our equation sheet, our value of the y-intercept for the regression model, which would be equal to f naught in this case, is going to be y bar, which is the average of the data points for y or for f. 27 plus 79 plus 210 divided by 3 minus a 1, which is the 261.54 that we found, multiplied by x bar, which will be 0.1 plus 0.3 plus 0.8 divided by 3. If we do that math, we get that f naught is ending up being equal to 0.7179 newtons, rounded to 4 sig figs. Okay. Assuming that the force versus displacement data is stored in MATLAB under the variables f and x respectively, what single line of code finds the coefficients of the linear model? This is strictly just remembering polyfit. We're going to do polyfit of x, f, and then the last entry into that is the order of our regression curve, which for a linear model, that order is equal to 1. And that is our answer for that question. That's the end of question 2. A lot of plug and chug. Up here was more plug and chug. This is really just testing if you knew the equations or not. That part E was seeing if you knew MATLAB. All right, last part. An engineer has determined that the solution to an unknown system of equations is capital X is equal to XY 1, 2. They have already completed part of the LU decomposition process and are working with the following equation. LZ is equal to B. I give you L. I give you B. You need to tell me in part A, what is the matrix Z? This is super easy. I'm pretty sure this summer semester, this part A had 100% completion, which is great. So we're going to multiply the first row by the first column. That would be 1 times Z11 plus 0 times Z21 is equal to 4. You get that Z11 is equal to 4. You get 2 Z11 plus Z21 is equal to 10. We just found that Z11 was 4, so this is 8. We get that Z21 is equal to 2. So our Z matrix is going to be 4, 2 for part A. Now, knowing the solution to the system of equations, find the upper matrix U. Assume that U12 is equal to 1. So now we're making a step. Let's think about our LU decomposition process. We originally have AX equals B. A is going to be rewritten as LUX is equal to B. And then we end up with LZ is equal to B, which is what we started with at the top. And we just found Z. What I do know is that UX is equal to Z. So now I want to find the upper matrix U. So the upper matrix U, let's talk about this conceptually a little bit. That is the result of forward elimination of Gauss, which means that this lower triangle here, which for a 2 by 2 is just the bottom left element, and we know it's 2 by 2 considering that the L matrix is 2 by 2, and the fact that this is a system of equations with 2 unknowns. This would be something like U11, U12, U22, multiplied by X, which I gave in the problem. That's going to equal Z11 and Z21. So let's go ahead and use the things that I gave you. U11 we do not know. U12 I told you to assume is 1, and we do not know U22. XY I gave you as 1, 2. And the Z value is 4, 2. That's what we just found in part A. And now we can find our 2 missing U variables. I have U11 times 1 plus 2 is equal to 4. That's the top. That's this row multiplied by this column. I get that U11 is equal to 2. And then for the bottom row, I do 0 times 1, and then 2u2 is equal to 2. We get that u22 is equal to 1. Which means that our upper matrix, based on that assumption that u12 is 1, is 2, 1, 0, 1. That is our answer for part B. Based on the information provided and or found, write out the original system of equations in terms of x and y, and I tell you not to put it in a matrix. Remember that our original equation that contains our system is always going to be of the form ax equals b. But a is going to be the same as L times U. And I gave you L, and you just found U. So now we're going to multiply L and U together. So let's go ahead and find what L is. That was 1021. 1021. And then U is what we just found is 2101. Let's multiply this together to get A. If we do row 1 by column 1, we get 1 times 2 plus 0 times 0. If we do row 1 and column 2, we get 1 times 1 plus 0 times 1. We're going to get 1. We're going to get 2 times 2 plus 1 times 0. This is going to give us 4. Then we're going to do 2 times 1 plus 1 times 1. That gives us 3. I'm going to double check my math there. 2, 1, 4, 3. That seems good. And this would be 2, 1, 4, 3 times x, y is equal to b, which I also gave you in this problem, is 410. That would be writing the system of equations in a matrix form. If we were to do it as an actual equation, this would be 2x plus y is equal to 4. 4x plus 3y is equal to 10. And that is our answer. And we can check our work because right when the problem started, I gave you what x and y are. X and 1 is y is 2. X equals 1, y equals 2. If we plug those in, does that work? 2 times 1 plus 2 is 4. 4 times 1 plus 3 times 2 is 4 plus 6 is 10. That does work. This has to be the correct system based on the points that I gave you. Last part, use the inverse of matrix A to solve AX equals B. So we have 2, 1, 4, 3. X, Y is equal to 4, 10. And I ask you to use the inverse of A to find what X and Y is. And remember, all we're going to do in this situation is we're going to multiply both sides by the inverse on the left, because that'll give us the identity matrix times X is equal to the inverse times B. And that will give us our answers for X. So we have to find the inverse first on the equation sheet for a 2 by 2. This is 1 over the determinant of A times switching the diagonal values and taking the negatives of the off-diagonal values. The determinant, which I don't think I give you on the formula sheet, you have to know that, is 2 times 3 minus 4. So 6 minus 4. We're going to switch D and A, which will end up giving us a 3 and a 2. And then we'll keep the B and the C in the same position, but we'll just make them negative. This ends up being a half times those numbers, which will give us 1.5, negative 0.5, negative 2, and 1. 1.5, negative a half, negative 2, and 1. That is the inverse. Go ahead and erase some of this math here so that we have some space. This is A inverse. To find X, I'm just going to take A inverse. And multiply it by B. This is a 2 by 2 multiplied by a 2 by 1. The inner indices match. I can multiply. The outer indices become my size. So it's going to be a 2-row by 1-column answer. We're going to do 1.5. Oops. We're going to do 1.5 times 4, which is 6, plus negative 0.5 times 10. That's negative 5. 6 plus negative 5 is going to end up being a 1. Repeating, we're going to have to take this row and this column. So we'll do negative 2 times 4 is negative 8 plus 10. That gives us positive 2, and that matches what's expected. This one, at least in this semester, we're in the fall of 2025, is in note set 19, which is not on the exam, but I'm going to do it anyway just for future reference, where I want you to go ahead and derive an equation that finds the optimal value of b without a transformation. This is going to be the least squares method. We're going to plug in our function in yi minus f of xi. We'll square for the sum of the squares of our residuals. We're going to take the partial with respect to b, because that is the value we're looking for our optimization. It's going to be 2yi minus be to the 2xi. That inside stays the same. We multiply by the derivative of the inside. If we're taking it with respect to b, we end up with negative e to the 2xi coming out. Because again, if we're taking it with respect to b, that has no b. It goes away. In this term, the e to the 2xi is a constant because we're taking the derivative with respect to b. So that is what remains there. And we're going to set this equal to 0. Now this 2 can end up going away. This negative sign can end up going away. So I'm going to write this as the summation of yi e to the 2xi minus be to the 4xi is equal to 0. We can separate those and bring one of them over to the other side. I factored out the b. I can get that b is the summation of yi e to the 2xi divided by the summation of e to the 4xi, which is our answer for that problem. I apologize for the long video, but I hope the chapters at least allowed you to jump around and stuff and make you not watch this whole thing unless you needed it. If you have questions, let me know. I appreciate you watching. Good luck studying. I'll talk to you soon. Bye.